We will start the program with a basic understanding of what is an image, what is image processing, and the background about Opencv. An image is defined as a two-dimensional function f of x, y, where x and y are spatial or plane coordinates, and the amplitude of f at any pair of coordinates x, y is called the intensity of the image at that point. When x, y, and the amplitude of f are all finite discrete quantities, we call it as a digital image. The field of digital image processing refers to processing of digital images by computers. A digital image consists of finite number of elements, each of which has a particular location and value, which are referred as picture elements, image elements, and pixels. When an image is generated from a physical process, its values are proportional to the energy radiated by a physical source, basically electromagnetic waves. Hence, f of x, y must be non-zero and finite. That is, f of x, y lies between 0 and infinity. The function f of x, y is characterized by two components: illumination component ix, y, which is nothing but the amount of illumination on the object, and the reflectance component r of x, y, which is basically the amount of illumination reflected by the object. F of x, y is equal to I of x, y into r of x, y. We have already seen that f of x, y lies between 0 and infinity, and r of x, y lies between 0 and 1. When r of x, y, that is, when reflectance component is 0, we have total absorption, and when it is 1, we have total reflectance. The nature of I of x, y is determined by the illumination source, and Rx, y is determined by the characteristics of the imaged objects. We will be using Opencv extensively in this program. Opencv stands for Open Source Computer Vision Library. It's a huge toolbox that programmers can use to help computers see and understand images and videos just like humans do. It was created by Intel way back in 1999 and was written in C++ programming language. The main aim of Opencv is to make it easier for people to create applications that involve computer vision. That is, programs that can understand and analyze images and videos. Opencv is not just for C++ programmers. People who use Python and Java can also use it, and it works on many different operating systems. Today, Opencv supports a lot of different algorithms. These are like the individual tools in the toolbox. In total, Opencv offers over 2,500 algorithms. These include both traditional tools and the very latest ones for a wide range of computer vision tasks. With OpenCV, you can do a lot of things with images. You can filter them to enhance certain features, change their shapes, manipulate their colors, create histograms for analysis, and many more. We are going to be doing all of this and more in the rest of the program. In this session, you will learn how to read and write an image. When I say write an image, I am referring to saving the image. Every image you see consists of two parts. One is the illuminance component. Think of this as the light that shines on an object. The other is the reflectance component, which is how much of that light is reflected off the object and captured by the camera or your eyes. Together, these two parts combine to form the image we see. Incidence component indicates where the light falls on the object you are looking at. That light could be from a lamp or a sun. The reflectance component is the light that bounces off the object and reaches our eyes or the camera lens. It is this reflected light that allows us to see the object. When you see something like 183, 275, 3, it is describing an image size and color details. The numbers 183 and 275 are the image height and width in pixel. The 3 stands for the 3 color channels used in digital images: red, green, and blue. Every color you see in a digital image is a mix of these 3 base colors. Lastly, when we talk of 2 to the power 8 different possibilities of intensity levels, it means there are 2 to the power 8 different levels of brightness for each pixel. It is like having a scale of 1 to 2 to the power 8, where 1 could be very dark, like a black pixel, and 2 to the power 8 could be very bright, like a white pixel. This variation in brightness levels helps to provide detail and depth in an image. Now, let us go ahead and execute the code. As far as the code is concerned, we import the necessary modules, which is CV2 and matplotlib. We then read the image file using cv2.imread, and then we are going to display the image. So it is a very simple set of code. Before executing the code, we need to bring the image file into Colab's folders. So we will click that, then access the upload option and choose birds file, because the image in question is birds.jpg. Let's copy the folder path, rather the file path, and indicate in cv2.imread, and let's click the play button, which is for execution. We see an error message. What is the mistake we did? We didn't put the quotes. Now let's run. We should be able to see the results. Before we go and look at writing an image, I would like to ask a question. Why are we using matplotlib? We have the computer vision library CV2 that takes care of image processing tasks like reading, manipulating, and many different processes. If CV2 can take care of reading an image, can't it be used to display the image? That is the question I am asking you. If you see, we are using Google Colab as the development environment. In Google Colab, you cannot use cv2.imshow to display an image as you would in a typical local Python environment, because Colab is a cloud-based development environment and doesn't support the GUI operations. GUI means graphical user interface operations required by cv2.imshow. Instead, you can use matplotlib to display the images. If you are using some other development environment, you can very well display the image using cv2.imshow. Now we are going to write an image, that is, save the image. We are going to save this image under a different name. Please note that we have these different formats that are available to us for saving the image. You need to be aware of two things when it comes to saving an image: lossy compression and lossless compression. Lossy compression reduces the file size by eliminating certain information or details in the image. Think of it like downsizing your wardrobe. You might decide to get rid of some clothes that you rarely wear to save space. Once you have given away those clothes, you can't get them back. They are gone forever. Similarly, when you use lossy compression, Some details are discarded and cannot be restored. The more you compress the image, the more details are lost, which can eventually lead to a noticeable decrease in image quality. On the other hand, lossless compression is like a magic closet that can make your clothes take up less space but without actually getting rid of anything. When you need your clothes back, you can take them out of the closet and they are exactly the same as before. With lossless compression, every single detail of the image is preserved, no matter how many times you compress or decompress it. However, this kind of compression can't reduce the file size as drastically as lossy compression can. So, in summary, lossy compression can significantly decreases file size, but with a possible reduction in image quality. Lossless compression maintains the exact original quality but doesn't reduce file size as such. Which one you choose depends on what is more important for your specific needs. Is it storage space or is it image quality? When I run this snippet of code, the output I get is true and this image gets saved here. You can then download this image and use it for your other needs. In this session, we will transform the color image. The purpose of converting an image from RGB to grayscale is to simplify computations. A grayscale image requires less processing power and memory than a color image because it only has one color channel and not three. When converting from RGB to grayscale, each pixel's grayscale intensity is typically calculated as a weighted average of its R, G, and B intensities. That is 0.299R plus 0.587G plus 0.114B. These specific weights are used because the human eye is more sensitive to green light and less sensitive to red and blue light. So the green component is given more weight in the calculation to align with the human perception. The formula 0.299R plus 0.587G plus 0.114B is a widely used standard for converting an RGB image to grayscale. It is not just an arbitrary example of a weighted average. The specific weights in this formula are based on the luminosity method, which align with human perception. According to this method, green light contributes the most to the intensity perceived by the human eye, followed by red and then blue. These weights are calculated based on the standard reference for human vision sensitivity to colors and approximate the relative contributions of red, green, and blue to the overall perception of luminance. These weights, in fact, correspond to those defined in the recommended standard 601, a specific set of standards established for broadcasting. But it is important to note that these weights might not be optimal for all images and purposes, and sometimes other conversion methods or weights might be used depending on the specific needs of a project. When it comes to the coding for color transformation, we first import the necessary modules and then read the image. Then we use a function from the Opencv library to convert an image from color to grayscale. The image data in data is converted from blue, green, red or BGR. BGR is the color order used in Opencv. We convert from BGR to grayscale. The grayscale image is stored in IMG. Next, we split the color image into its three color components, blue, green, and red. After this, B, G, and R are each a two-dimensional matrix of size m by n, where each element in the matrix represents the intensity of that color in the corresponding pixel of the image. Next, we concatenate or join side by side the three color component images and the grayscale image to create a new image. Finally, we display this new image using Matplotlib's pyplot with a title for each part of the image. There are a number of benefits to do color transformation. Grayscale images are simpler to process than color images because they only have one color channel compared to three channels in a color image, that is red, green, and blue. This makes many image processing and computer vision tasks faster and less computationally intensive. Highlighting certain features in an image might be certain features in an image might be easier to detect in grayscale or another color space. For example, edges can be easier to detect in grayscale because edges correspond to changes in brightness, which are often important in image analysis. Some image processing algorithms work better or can only work with grayscale images or images in a certain color space. For example, some algorithms for object detection, segmentation, or feature extraction may require grayscale images. If the color of the image is not important for the task at hand, converting to grayscale can help to prevent the model from learning spurious correlations based on color. Last but not the least, grayscale images take up less storage space and memory, which can be important for large scale processing. So, in summary, the transformation of image colors is a commonly used step in image processing that can simplify computational tasks, highlight certain features, and prepare images for further processing. Adding two images, sometimes referred to as image blending or image fusion, is a common operation in image processing for a variety of reasons. By adding two images, we can combine different pieces of information from each. For example, one image might have better detail in darker regions and the other in lighter regions. Adding them together can create an image that has good detail across all light levels. Adding two images can create interesting special effects too. For example, in digital photography and film, multiple exposures are often added together to create artistic effects. Another important area is noise reduction. If you have several noisy but otherwise identical images, adding them together can help reduce the noise. This is a common technique in astrophotography where multiple images of the night sky are added together to increase the signal to noise ratio. In medical imaging or geographical information systems or GIS, images from different sources like an MRI and a CT scan or a satellite image and a topographic map might be added together to overlay information. We will use the CV2.addWeighted function, which is a weighted sum of the images, a linear blend basically. This can be used to decrease or increase the influence of the respective images on the result and can even involve negative weights, potentially useful in algorithms to highlight the differences between two images. Now, for doing the arithmetic operations, we will be using CV2 and Matplotlib. CV2 for image processing and Matplotlib for displaying the images. We start by reading the images and then converting the images to grayscale using CV2.CVT color. We then resize the images using CV2.resize for optimal processing. We will use the CV2.addWeighted function, which is a weighted sum of the images, a linear blend. The addWeighted function takes in two images, assigns a certain weight to each image, and then adds them together. In this case, image 1 is being weighted by 0.5 and image 2 is being weighted by 0.4. The last parameter 0.6 is a scalar added to each pixel after the weighted addition. So for each corresponding pixel in the two images, the resulting image pixel value is the result of the equation that you see on your screen. We now concatenate the two original grayscale images and the resulting image from the weighted addition horizontally, that is side by side, into a single image. Finally, we use plt.hist to display the histogram. A histogram is a graphical representation of the tonal distribution in a digital image. It plots the number of pixels for each tonal value, providing a way to visualize the distribution of pixel intensities or brightness values in an image. For a grayscale image, the histogram will be a single curve since there is only one channel. But for a color image, you would typically see three overlapping histograms, one each for the red, green, and blue color channels. When we add two images and show the histogram of the resulting image, the histogram provides a visualization of how the pixel intensities in the combined image are distributed. This can give us insights into how the combination of the images has affected the overall brightness and contrast of the resulting image. By comparing the histograms of the original images with the histogram of the combined image, which is what we are doing here, we can see how the operation of adding the images has affected the distribution of pixel intensities. For example, if the operation has increased the overall brightness of the image, we would see a shift to the right in the histogram of the combined image. Just like how we added the two images using cv2.addWeighted function, we can also subtract using cv2.subtract. Subtraction of images, often called image difference or image subtraction, is a common operation in image processing. This operation is performed on a pixel by pixel basis. That is, the value of the pixel in the output image is the result of subtracting the corresponding pixel values in the input images. There are many applications of image subtraction. By subtracting successive frames in a video, you can detect the areas of the frame that have changed. In other words, the areas of motion. This is a common technique in surveillance and security systems, as well as in video compression algorithms. In fields like remote sensing or medical imaging, image subtraction can be used to detect changes in a scene or an anatomical structure over time. For example, satellite images taken at different times can be subtracted to reveal changes in land use or climate. Similarly, subtracting medical images like MRI scans taken at different times can show the growth or shrinkage of tumors. If you have two very similar images and want to highlight their differences, you can subtract one from the other. The resulting image will be black or close to black in areas where the images are the same and brighter in areas where they differ, as you are seeing in this particular image. In image processing, the AND, OR, and NOT operations typically refer to bitwise operations performed on the pixel values of binary or grayscale images. They are also used in the context of image mask. Now let us start with AND operation. The AND operation is performed on a pixel by pixel basis between two images or an image and a mask. For each pixel, if the corresponding pixel values in both images are true, that is non-zero, then the output pixel will also be true. Otherwise, the output pixel will be false or zero. In the context of a mask, the AND operation can be used to retain only the portions of an image that correspond to the non-zero regions of the mask. And is used in image masking and background subtraction. In the case of image masking, we want to isolate a particular region of interest in the image. The operation retains the parts of the image where the mask is set to true and sets the rest to black or zero. Bitwise and can be used in background subtraction, a technique used in motion tracking and object detection. We subtract the current frame from the background frame and then use AND, that is, AND it with a binary thresholded version of the same difference image to enhance the objects in motion. The OR operation is also performed on a pixel by pixel basis. For each pixel, if the corresponding pixel value in either of the images is true, then the output pixel will also be true. If both are false, the output pixel will be false. This can be used to combine the non-zero regions of two images or masks. OR operation is useful in image merging and adding watermarks. The OR operation can be used to merge two binary images where the resulting image will have all the non-zero regions of both input images. If you have a binary image that serves as a watermark and another image where you want to add this watermark, you can use the OR operation to accomplish this. The NOT operation is a unary operation, meaning it operates on a single image rather than two. It inverts the pixel value of the image. True values, that is non-zero, become false or zero, and false values become zero. In the context of a mask, the NOT operation can be used to invert the mask, switching the regions to keep and the regions to discard. The NOT operation is used to obtain the negative of a binary image. It will turn white pixels to black and vice versa. This can be useful in various computer vision tasks, such as enhancing white or lighter objects in an image. If you have a mask and you want to invert the area of interest, that is, make the masked area of interest and vice versa, you can use the NOT operation. I wanted to cover the XOR operation also as part of this session. The XOR operation or exclusive OR is another bitwise operation that can be performed on images. XOR is a binary operation, meaning it operates on two images or an image and a mask. Like the and OR operations, XOR is performed on a pixel by pixel basis. For each pair of corresponding pixel in the two images, the XOR operation gives a true output, that is, a non-zero output, if the pixel values are different, that is, one is true and the other is false, and a false output, that is, zero output, if the pixel values are the same, that is, both are true or both are false. In the context of image processing, XOR can be useful in a variety of situations. By using XOR in two different binary images, you can create an output image that highlights the areas where the two input images differ. If you have two binary images that you want to overlay, that is, combine the true pixels from both images, XOR can be a useful operation. Unlike the OR operation, which would give a true output, if either input is true, the XOR operation will give a false output for pixels that are true in both inputs, thereby helping to avoid overlap. When it comes to coding, we use bitwise underscore and, bitwise underscore r, bitwise underscore not, and bitwise underscore xr to do these operations. Make sure to resize the image before doing the bitwise operations. Before concluding this session, I wanted to clarify a doubt that may be there in your mind between CV2 bitwise and and cv2.addWeighted. Please note, they are two different functions provided by the Opencv library that operate on images, but they perform quite different operations. cv2 bitwise AND is a function that performs a bitwise AND operation on the pixel values of the two input images. Bitwise AND operation takes 2 bits and returns 1 if both bits are 1, otherwise it returns 0. This operation is performed on every corresponding pair of pixels in the two input images. The resulting image will only keep the parts where both input images have a pixel value. This is commonly used for masking operations where you want to zero out certain parts of an image. In the case of cv2.addWeighted, this function performs a weighted sum of the two input images. This operation is also performed on every corresponding pair of pixels in the two images. The weights determine how much each image contributes to the resulting image. You can also add a scalar value to every pixel after the sum. This is commonly used for blending or merging images. In short, cv2.bitwise AND is a bitwise operation that is used for masking, while cv2.addWeighted is an arithmetic operation that is often used for blending. The choice between them depends on what you want to achieve with your image processing tasks. Masking and blending are two different operations that can be applied to images, and each has different purposes and results. If you are wondering what is masking and blending, let me explain this once again. A mask is a binary image consisting of 0 and non-zero values. The non-zero values indicate the region of interest, that is, the part of the image where we want to perform operations, and the zero values indicate the area to ignore. When a mask is applied to an image, only the pixels in the image that correspond to the non-zero regions of the mask are affected or visible in the output. Masking is used when you want to isolate or manipulate specific parts of an image. For example, in object detection, we might create a mask that isolates the object from the rest of the image. Image blending, on the other hand, is the process of combining two or more images in a way that produces a smooth transition from one image to another, creating a composite image. The contribution of each image to the final result is controlled by assigning weights to the images. The weights can be uniform or they can vary across the image. For example, in panorama stitching, we might blend the overlapping parts of image so that there is no visible seam between them. In short, masking is used to isolate or hide parts of an image, while blending is used to merge multiple images smoothly. Both techniques are crucial in image processing and computer vision tasks. In this session, we are going to look at image rotation, image flipping, and increasing the brightness of image. We will start with image rotation. This is the image which we are going to rotate. This is a color image, so we are going to convert that into grayscale because grayscale is more efficient. And then I use cv2.rotate to rotate the image. Here I am rotating by 90 degrees and clockwise. We can mention the extent of rotation we want here. Finally, I display the original image and the resultant image. For that, I concatenate the two images. I'm using concat instead of using IMShow to display the original image and the rotated image. Because when I use IMShow, the final output will override the earlier input which I want to display. So this is the output we have. This is the rotated image, 90 degrees clockwise, and you can see that in the shape value also. Next, we move to flipping. We can either do horizontal flip or vertical flip. In this case, we are going to do vertical flip. So I'm using cv2.flip, the image in question, and I indicate the vertical flip with 0. Okay. This is the image that I'm going to flip. As far as the code is concerned, we start by reading the file first, then converting the color image into grayscale and resizing it for optimal processing. We then flip by indicating this particular file and we give a value of 0 because we want this to be a vertical flip. We then concatenate because we want to show both the original image as well as the resultant image. And you can see here the person who is using the keyboard and the mouse is appearing on the opposite side in the resultant image. Okay. As far as the other options are concerned, that is, what can I use instead of 0? And how do I do an horizontal flip? So you use 1. 1 is for horizontal flip, that is flipping along the y-axis. 0 is for vertical flip, that is flipping along x-axis. You also have the option for -1, which is nothing but flipping the image both vertically and horizontally. That is, the image rotates 180 degrees. Here, the image rotates along the x-axis. Now, we are going to increase the brightness of this particular image. As in the previous scenarios we saw, we are going to first read the image, then convert it into grayscale, and then resize for optimal processing. If you see the process of enhancing the brightness, I merely add a number plus 40. I can also reduce it. Here I need to use minus 40. That's all. Instead of plus 40, if I use minus 40, I'm reducing the brightness. Since I have converted a color image into a gray image, I can easily add plus 40. If it is red, green, blue, it is difficult to add plus 40 like what you're seeing, because then it becomes a three-dimensional matrix. To add a number to the three-dimensional matrix, that is a slightly complicated process, whereas this one is fairly straightforward. You have an image, you have converted it to grayscale, you can go ahead and add a number and that will increase your brightness. It's as easy as you can think of. And once you have increased the brightness, you can use concat, okay, so that you can display both the original image as well as the resultant image. All these places, the brightness is enhanced. You can see that visually when you compare the two images. Image resizing is a common operation in image processing that changes the dimension, which is width and height of an image. It can be used to reduce the size of an image, to save space or processing time, or to increase the size of an image for purposes such as printing or detailed analysis. Linear interpolation and nearest neighbor interpolation are two methods used for resizing images, particularly when the image size is being increased and new pixel values need to be estimated. Linear interpolation is a more complex method that computes the value of new pixel based on weighted average of the nearest pixels. Specifically, for a grayscale image, the pixel intensity value at a new location is a weighted average of the intensities of the 4 pixels surrounding that location. For a color image, the process is applied separately to the red, green, and blue channels. Linear interpolation leads to smoother gradients and avoids the blocky appearance that nearest neighbor interpolation can produce. Nearest neighbor interpolation is the simplest method and simply assigns the value of the closest pixel to the new pixel. Specifically, it considers the pixel that falls within, that is the nearest pixel, and uses that pixel's value. This method is fast but can produce a blocky appearance because it does not consider any other pixels other than the closest one. When it comes to code, here we are trying to read the image and then we convert the image to grayscale. We then apply linear interpolation using CV2.resize. We access the width and height, and then we multiply both height and width by 2, and we can see the result when it comes to the axis between the original image and the resized image. We then apply the nearest interpolation. Here it is linear interpolation. Here it is CV2 dot inter underscore nearest. So that does the nearest interpolation for resizing the image. The output is nearly the same because the image is fairly simple and straightforward. To summarize, linear interpolation generally provides superior results because it considers more context by using a weighted average of nearby pixels. However, it is also more computationally intensive than nearest neighbor interpolation. The choice between these methods depends on the specific requirements of your application, such as the acceptable trade-off between image quality and computational efficiency. Image blurring, also known as image smoothing, is an image processing technique used to reduce noise and detail in an image. It can also be used for creating a blur effect. Image blurring, also known as image smoothing, is an image processing technique used to reduce noise and detail in an image. It can also be used for creating a blur effect in images. Blurring is achieved by convolving the image with a low pass filter kernel. This process works by averaging the pixels in a neighborhood around a pixel in the input image and setting the corresponding pixel in the output image to that average. The result is that sharp edges and high frequency details get blurred. There are several types of blurring techniques. Box blur simply takes the average of all the pixels surrounding a pixel in the kernel area. Gaussian blur uses a Gaussian kernel instead of a box shaped kernel. The idea is the same, but the pixels are averaged in a different way. The pixels closer to the center of the kernel have a higher weight, resulting in a more natural blurring effect. Median blur is effective when trying to remove salt and pepper noise. Instead of averaging pixel values, the median values in the kernel window becomes the output value. Last but not the least, bilateral blur is a more advanced type of smoothing filter that preserves the edges while smoothing the image. It considers both the neighboring pixels as well as the intensity differences, reducing noise and preserving the high frequency components. In all these methods, the size of the kernel and the standard deviation in case of Gaussian and bilateral blurs determine the extent of the blurring effect. Large kernels and high standard deviation result in more blurring. This is the image we are going to blur, and we are going to apply Gaussian, median and bilateral blur. We will be using CV2.Gaussian blur, CV2.median blur and CV2.bilateral filter to see the effects of blurring across the three techniques. I have also included the original so that you can compare. Before using the image blurring library that is part of CV2, make sure that you convert the image to grayscale for efficiency and resize for optimal working. This line applies a Gaussian blur to the grayscale image. The size of the Gaussian kernel is 3 by 3 and the standard deviation in the x and y direction, sigma x and sigma y, is set to 0. When sigma x and sigma y are set to 0, they are computed from the kernel size. The resulting blurred image is stored in Gauss underscore blur. The next one, median blur. This line applies a median blur to the grayscale image. The size of the kernel is 5. The median blur uses the median of all the pixels under the kernel window, and the central pixel is replaced with this median value. This is highly effective, as I said earlier, in removing salt and pepper noise. The resulting blurred image is stored in med underscore blur. The third one, bilate underscore blur. This line applies a bilateral filter to the grayscale image. The bilateral filter is a non-linear edge preserving and noise reducing smoothing filter. The size of the pixel neighborhood is 9. The sigma color, filter sigma in the color space is 75, and the sigma space, filter sigma in the coordinate space is also 75. The resulting blurred image is stored in bilate blur. So this is how we go about the process of blurring the image. Image enhancement is the process of adjusting digital images so that the results are more suitable for display or further image analysis. The goal of enhancement is to emphasize unique features or characteristics in the image. Image enhancement techniques can be broadly divided into two categories: spatial domain methods and frequency domain methods. Spatial domain methods operate directly on pixels. The pixel values are manipulated to achieve desired enhancement. For example, log transformations, power law transformation, which is the gamma transformation. We are going to see that. Histogram equalization, that is also something we are going to see. They all come under spatial domain methods. Frequency domain methods operate on the Fourier transform of an image. The image is first transformed into frequency domain. Manipulations are done on the Fourier transform and then transformed back. Okay. Now let us look at gamma correction, okay, which is one of the image enhancement techniques. This is also known as power law transformation. This technique is used for controlling the brightness of an image by altering the pixel values. A gamma value less than 1 brightens the image, a value greater than 1 darkens the image, and a value of 1 leaves the image as is. It is useful in situations where an image is either excessively dark or excessively bright. We will be using this particular equation for the purpose of image enhancement. How the image enhances for different values of gamma is shown in this graph, and it is also represented in the form of the improvement that we note in images. The next one is histogram equalization. This is a method to adjust image intensities to enhance contrast. It operates by effectively spreading out the most frequent intensity values or stretching out the intensity range of the image. The idea of histogram equation is to map the original distribution of pixel intensities to a uniform distribution so that each intensity value is equally probable. This increases the global contrast of many images, especially when the usable data of the image is represented by close contrast values. The next one that we are going to see is an extension of the histogram technique. It is known as contrast limited adaptive histogram equalization, CLAHE. This technique is a variant, as I mentioned, of adaptive histogram equalization, in which the contrast amplification is limited, reducing noise in the output image. CLAHE operates on small regions in the image called tiles rather than the entire image. Each tile's contrast is enhanced so that the histogram of the output region approximately matches the specified histogram. The neighboring tiles are then combined using bilinear interpolation to eliminate artificially induced boundaries. This method is suitable for improving the local contrast and enhancing the definition of edges in each region of an image. It is generally used in medical imaging and industrial inspection to enhance small details in an image. Now let us look at the code that we can use for image enhancement. The image that I'm using is the image where someone is working in front of a computer using keyboard and a mouse. Okay, a laptop is also nearby to the external monitor. So it is the image that we are trying to enhance. The process starts with reading the image, then converting the color image to gray, and then resizing. This is something that we did earlier also. And then we go ahead and enhance the image using a gamma value of 0.1. Okay, so these two lines of code pretty much does the job of enhancing the image. Rest of the code is basically to display the original image in grayscale and the adjusted image. We are also trying to show the histogram of the adjustment so that you can see the change in the pixel value and the frequency, right? And for this, we are using matplotlib. So that is all we are doing in this set of codes. Instead of the gamma, I can also use the in the histogram technique, I can use equalize hist. Okay, this is one option. So instead of these two lines of code, I can use this, or I can use this. This is for CLAHE. Okay, as I mentioned earlier, CLAHE is very efficient when you want to detect minor details. So it is very helpful in medical images. The clip limit that you see here is a commonly used value. The clip limit parameter sets the threshold for contrast limiting. If the histogram bin is above this limit, the pixels are clipped and distributed uniformly to other bins before applying histogram equalization. In this session, we are going to look at noise and denoising model. Noise introduction and denoising processes are often used in machine learning, specifically in the domain of image and signal processing, but can be applied in other data types as well. The two primary components are noising and denoising. Noising is a model or function that intentionally adds noise to the data. It can be used to simulate real-world scenarios where data may be corrected by various sources of noise. For example, a noising model could add Gaussian noise to an image, simulating the effect of a poor quality camera sensor. This is commonly used in training to create robust models by augmenting the training dataset. Denoising model, on the other hand, is a model designed to remove the noise from the corrupted data and restore it as closely as possible to its original uncorrupted state. Denoising models are extensively used in image and signal processing to improve the quality of data. They can be designed using various techniques such as deep learning. When I say deep learning, we can use convolutional neural networks or autoencoders. We can also use wavelet transforms. One of the more common uses of these two is in the concept of denoising autoencoders. A denoising autoencoder is a specific type of neural network that is trained to remove noise from the corrupted data. During training, a noising function is applied to the input data, and the model learns to reconstruct the original uncorrupted data from the noisy input. This has been shown to improve the robustness and generalization of the model. In a broader sense, this concept is part of a larger theme in machine learning of training models to be robust against various forms of corruption in the data. Noise injection at training time can be seen as a form of data augmentation or as a form of regularizer, preventing overfitting by providing a harder training task. The denoising step then learns to recover from these specific corruptions, which can often generalize to unseen corruptions as well. Now let's look at Gaussian and speckle noise. that are used in noising models. Gaussian noise, also known as white noise, is a type of statistical noise having a probability density function equal to that of a normal distribution, which is also known as the Gaussian distribution. In other words, the values that the noise can take on are Gaussian distributed or normally distributed. This means the noise in each pixel is independent of the color information in the pixel and is randomly spread throughout the data. In images, Gaussian noise tends to appear as speckles in otherwise smoothly colored regions and is typically caused by sensor noise and poor illumination. In the context of a noising model, adding Gaussian noise to an image might involve adding a random value drawn from a Gaussian distribution to the intensity of each pixel. This can make the model more robust to such noise in the real world. Speckle noise, on the other hand, is a granular interference that inherently exists in and degrades the quality of the active radar and synthetic aperture radar SAR images. Speckles are essentially caused by the inference of multiple signals produced by the minute distribution of targets within each resolution cell. In simpler terms, speckle noise in an image represents the presence of salt and pepper type noise, where some pixels are highly illuminated and others are very dark, occurring in granular salt and pepper patterns. In the context of noising model, adding speckle noise to an image might involve multiplying the intensity of each pixel by a random value drawn from a certain distribution, often a Gaussian distribution. This can make the model more robust to such noise in the real world. Both types of noise are common in real world situations, and training models to handle them can be very beneficial for their performance on real world tasks. Now, let us look at the code that we are going to use for noising model, and we are going to start with Gaussian noise model. The code structure is very similar to the one that we have followed earlier. We read the image, we then convert the image to grayscale, and we then resize the image. Okay. We then apply the Gaussian noise model through these 3 lines of code. The rest of the code is for displaying the original image and the changed image. And we also display a histogram that will correspond to the original and the resultant image. That's what the rest of the code does, and we are accomplishing this through the help of matplotlib.pyplot. Okay, the core set of codes that we are using in Gaussian noise model is these 3 lines of code. This line generates Gaussian noise. The numpy.random.normal function draws random sample from a normal or Gaussian distribution. The first argument is the mean of the distribution, second argument is the standard deviation, and the third argument is the number of samples you want to draw. In this case, it is generating samples which equals the total number of pixels in the grayscale image from a normal distribution with a mean of 0 and a standard deviation of 1. Each sample represents noise for a single pixel. The second line that you see here, this helps to reshape the one-dimensional Gaussian noise array GN into the same shape as the image img underscore gray. So if img underscore gray is a 100 by 100 pixel image, GN will become a 100 by 100 matrix, where each element represents noise for a corresponding pixel in img underscore gray. The as-type uint8 function is converting the data type of GN to 8-bit unsigned integer format. This is the standard format for images where pixel intensities range from 0, which is black, to 255, which is white. The third line that you see here, this adds the Gaussian noise GN to the grayscale image on a pixel by pixel basis to generate a noisy image. CV2.add is used instead of the normal addition operator plus because it performs saturated arithmetic. That is, if the result of an addition operation is greater than 255, it will be clipped to 255 instead of overflowing. So in summary, these lines of code are generating a noisy version of a grayscale image by adding Gaussian noise to it. So after the addition, we see the original image and adjusted image. As you can see, there is quite a bit of noise in this image, and we are seeing that in the resultant histogram as well. We will use these three lines of code when we want to use speckle noise. The expression that you see here is different from the expression here. The expression here would not add Gaussian noise in the same way as this expression. Instead, it performs a different operation entirely. This expression would not add Gaussian noise in the same way as this expression. Instead, it performs a different operation entirely. img underscore gray into gn performs element-wise multiplication of the grayscale image and the Gaussian noise. This operation modifies the intensity of each pixel in the image based on the corresponding Gaussian noise value. As a result, this operation amplifies the pixel intensities rather than adding noise to them. If you want to add noise to the image, it is more common to add the noise directly to the pixel as we see here rather than this particular option. Now we will look at denoising models. Denoising models often use filters to remove noise from images. The type of filter used depends on the type of noise present in the image. Let's start with Gaussian filtering. Gaussian filtering is often used to blur an image or to reduce detail and noise. It works by convolving the image with a Gaussian function. The result is a smooth blur that looks very natural to the human eye because the pixels in the image are averaged with their neighbors in a way that nearer pixels influence the average more than the distant ones. Gaussian filters are often used in reducing Gaussian noise and are also used for achieving a smoothing effect in an image to reduce details. Due to the nature of the Gaussian function, the filtering effect preserves the edges in the image since the intensity change across edges is gradual and not abrupt. The next one is average or mean filter. The average or mean filter works by moving through the image pixel by pixel, replacing each value with the average value of neighboring pixels, including itself. This neighborhood is usually square, like 3 by 3, 5 by 5, or 9 by 9 that you see on your screen. The average filter is a simple and intuitive filter that is often used for general noise reduction. However, it tends not to preserve edges very well. The larger the neighborhood, the more an edge gets blurred in the output. Last but not the least is the median filter. The median filter is a non-linear digital filtering technique often used to remove noise from an image or signal. Like the mean filter, the median filter considers each pixel in the image in turn and looks at its nearby neighbors to decide whether or not it is representative of its surroundings. Instead of simply replacing the pixel value with the mean of neighboring pixel values, it replaces it with the median of those values. The median is much less sensitive than the mean to extreme values or outliers. Therefore, the median filter is much better at preserving sharp edges while removing noise, and it is particularly effective at removing salt and pepper type noise. Each of these filters has its own strengths and weaknesses, and choice of filter depends on the specific task, specific image, and the specific type of noise you are trying to remove. Now, let us look at the code for the Gaussian based denoising model. As in the previous scenarios, we are first going to read the image, convert it into grayscale, and then resize. Before that, we import the necessary libraries. The core set of codes for denoising is these two lines of code. The rest of the codes are for displaying the image side by side, that is the original and the resultant image, and the associated histogram. Let me zoom the core set of codes that we are using for denoising. Let me zoom it. This code generates Gaussian kernel of size 3 and standard deviation of zero point 0.9. This code applies the generated kernel onto the image. We can see the original and the resultant image, and the adjusted image, we can clearly see the noise has been removed. And this is depicted in the histogram as well. The histogram is a plot of pixel values and frequency. If we use averaging based denoising filter, we need to adjust the code. Here, W is equal to 5 indicates the window size. This sets the window size for the averaging filter to 5. This means that the kernel will be a 5 by 5 matrix. The next one that you see here, this line creates a 5 by 5 matrix filled with ones and then divides every element by 25, the total number of elements. This gives a 5 by 5 matrix where each element is 0.04. When this kernel is applied to an image, it effectively calculates the average of every 5 by 5 block of pixel. The next line applies the averaging filter to the image. The filter operation effectively replaces every pixel in the image with the average value of its 5 by 5 neighborhood based on the kernel, thereby smoothing the image. This kind of averaging filter can be very effective for reducing high frequency noise in an image. However, it also tends to blur edges and other high frequency details, so it is often used as a simple first pass noise reduction step before applying more sophisticated noise reduction algorithm. Instead of this one, we can also use the median blur. Before that, let's see the original and the adjusted image. The adjusted image is now free from much of the noise. Okay. Now coming to the median filter, instead of average, we use median. Median is free from exposure or impact to outlier and extreme values. I need to adjust the code with this. The function cv2.median blur applies a median blur to an image. The median blur operation replaces each pixel's value with median value of the pixels in its neighborhood. The earlier one used mean, now we are using median. So the size of this neighborhood is specified by the second argument to the function. This line applies a median blur to the image using a 5 by 5 pixel neighborhood. For each pixel in the image, it looks at the 5 by 5 block of pixels centered on that pixel, sorts these 25 pixel values because we need to sort in the case of median, and replaces the original pixel value with a median of these 25 values. This operation, that is the one using the median, is particularly effective at removing salt and pepper noise, which corresponds to random occurrences of black and white pixels. Unlike an averaging filter or Gaussian blur, a median blur can preserve edges in an image since median is not affected by few extreme values. Always remember this. As a result, if a pixel is on an edge, so that some of its neighborhood is on a bright region and some is on a dark region, the median is likely to be a value from the edge and not the bright or dark region. Morphological operations are a set of nonlinear operations that process an image based on its shape. They apply a structuring element like a small binary or grayscale image. You can think of this as a disk or a square to an input image to generate an output image. They are most commonly applied to binary images, but there are extensions for grayscale images as well. Morphology, in the context of image processing and computer vision, is a theory and technique for the analysis and processing of geometrical structures. It is specifically focused on the manipulation of the shape or morphology of features in an image, hence the name morphology. In this session, we are going to be looking at many of the morphological operations that you see on your screen, like dilation or erosion, set operations and logical operations, and many of the morphological algorithms like region filling, convex cell, and so on. The steps involved in morphological image processing start with inputting an image, reading it, creating a structural element, and then performing the morphological operations between the image and the structuring element. The last step is about extracting the resulting portion so that the structural properties of the object can be obtained. This is how we go about in the morphological image process. Morphological operations rely on the relative ordering of pixel values and not on their numerical values. A template or a structuring element is applied to the image to obtain or extract a portion of the image which represent a certain structure of an object. The structuring element can be a square 5 by 5 element, a diamond shaped 5 by 5 element, a cross shaped 5 by 5 element, or a square 3 by 3 element. The operations between the structuring element and the image can consist of set, arithmetic, or logical operations. For the purpose of image filtering applications, morphological operations are divided into dilation and erosion. Combining dilation and erosion together leads to image opening and closing operations. All these are covered subsequently. If you are wondering why we need morphological image processing, let's look at this particular table. This summarizes the key differences between morphological operations and common computer vision operations. Morphological operations are non-linear operations that process an image based on its shape. They focus on altering the structure of objects in the image. They typically involve operations such as dilation, which is expanding shapes, erosion, which is shrinking shapes, opening, which is removing noise and small objects, and closing, filling in holes and gaps. Morphological operations use a structuring element, a small binary or grayscale image, typically a square or a circle, that determines the precise nature of the operation. They are particularly well suited for binary images and tasks such as removing noise, separating overlapping objects, and morphological simplification like thinning. Now, let us understand common operations in computer vision as opposed to morphological operations. Many common operations in computer vision are linear operations. Okay, if you note the ones in morphological, they are non-linear. So many operations in computer vision are linear operations that alter the color, contrast, sharpness, and other visual properties of an image. The common operations in computer vision focus on adjusting pixel values rather than changing the structure of objects in the image. Common operations including blurring, sharpening, and edge detection. These operations, that is common operations in computer vision, often use a kernel, a small matrix of weights that is convolved with the image to produce the output. The common operations are applicable to all types of images and can serve a wide range of purposes from simple visual enhancement to complex feature extraction for machine learning models. So, in summary, while both morphological operations and common operations in computer vision involve applying a small matrix or structuring element to an image, they are fundamentally different in their goals and methods. Please note that the choice between them depends on the specific task at hand. Dilation and erosion are two fundamental operations in mathematical morphology, a theory and technique for the analysis and processing of geometrical structures. We are going to be using this image for demonstrating dilation and erosion. Let us look at the code. We first read the image. We then convert this color image into grayscale and resize it for optimal processing. For the purpose of dilation and erosion, we will be creating a kernel, which is a small matrix of size 10 by 10, where all the elements are 1. This kernel will be used in the morphological operations that follow. The data type of the kernel is an unsigned 8-bit integer. We then apply the morphological operation of erosion on the grayscale image using the kernel defined previously. Erosion essentially erodes away the boundaries of the object in the image. In terms of the effect, erosion decreases the white regions and increases black ones. White regions are of high intensity and black ones are of low intensity. The parameter iteration is equal to 1 indicates that the operation is done only once. Now, for applying dilation, we use cv2.dilate. So this applies the morphological operation of dilation on the grayscale image using the same kernel that we defined just now. Dilation is the exact opposite of erosion. It increases white regions and decreases black ones. Here also we set the parameter iterations to 1. This means that the iteration is done only once. That is, the operation is done only once. Finally, we concatenate the original grayscale image, the eroded image, and the dilated image horizontally. The result is a single image that allows you to compare the original eroded and the dilated image side by side. Matplotlib's IMShow function is used to display the concatenated image. The parameter cmap equal to gray specifies that the image is displayed in grayscale. We can perform erosion and dilation on color images too. In this case, the operations are applied independently to each channel, that is red, green, and blue of the image. Note that while Matplotlib's IMShow function expects images in RGB format, Opencv uses BGR format by default. That is why we are converting the final concatenated image from BGR to RGB before displaying it. The rest of the code is the same. Also remember that erosion and dilation can produce unexpected results on color images depending on the colors and shapes in the image and the size and shape of the structuring element. If you see this particular image, that is the eroded image, is totally black. We could address this issue by changing the kernel size. If the kernel used is larger than the objects in the image, it could potentially cause the output image to be all black. In such a case, we might want to try using a smaller kernel. Having seen the codes, let us try and understand the mathematics behind dilation and erosion. Given a binary image A and a structuring element B, the dilation of A by B can be defined with the help of this equation. So what is this equation? In simple terms, the dilation of A by B is the set of all points C such that the translated structuring element B underscore C has at least one point in common with A. What it is saying is the dilation of image A by the structuring element B consists of all the points where if you place the center of B at that point, there is at least one overlapping pixel between the image and the structuring element. This is the basic principle of dilation. If the structuring element fits at a particular location in the image, meaning there is at least one pixel of overlap, then the pixel at that location in the output image will be set to the foreground color, typically white, in a binary image. How do we correlate the symbols and the mathematical formula to the code? That's what I've attempted here. The symbols A, B, and C in the formula are abstract mathematical notations and do not directly translate to specific variables in the code. However, they do have conceptual equivalence in the code. A represents the input image. In the context of the code, this would be the image2 underscore grid. When it comes to B, B is the structuring element that is used in the dilation process. In the code, kernel represents B. C represents a generic point in the space of the image, typically each pixel. In the code, this would correspond to each individual pixel position in the image. Finally, the operation B underscore C intersection A not equal to 0 conceptually refers to placing the structuring element B at each location C in the image A and checking if there is any overlap. In the code, this operation is performed by dilation equals cv2 dot dilate, where Opencv's dilate function automatically handles the translation and intersection operations. When it comes to erosion, the erosion of A by B is the set of all points C such that the translated structuring element B underscore C is completely contained in A. So the effect of erosion on a binary image is to erode away the boundaries of regions of foregrounded pixels. That way, the isolated pixels that were originally part of the foreground become part of the background now. Image opening and closing are two fundamental morphological operations that are derived from the basic operations of erosion and dilation. They are especially useful for removing noise, isolating individual elements, and joining disparate elements in an image. Opening is an operation that consists of erosion followed by dilation. The purpose of opening is to remove small objects from the foreground of an image while preserving the shape and size of larger objects in the image. Closing is an operation that consists of dilation followed by an erosion. The purpose of closing is to fill small holes in the foreground of an image while preserving the shape and size of larger objects in the image. Closing first dilates the image to fill holes and then erodes it to restore the shape of the objects. In both the cases, A is the input image, B is the structuring element, and the operations are applied with respect to a given neighborhood around each pixel. It is important to note that the results of opening and closing operations are dependent on the shape and size of the structuring element used. When it comes to the code, the opening and closing are achieved with the help of cv2.morphologyEx. You can see this both in the opening codes as well as closing codes. cv2.morphologyEx is used to perform the morphological operations. The second argument to this function specifies the type of operation. cv2.morph underscore open is for opening and cv2.morph underscore close is for closing. The third argument is the structuring element used for the operation. The rest of the codes is fairly similar to the approach that we have taken in earlier session. where we first read the file, resize it for optimal processing, and then we try to display both the original and the changed images. In this session, we will look at morphological operations like boundary extraction, image filling, and finding contours of the image. We will start with boundary extraction. Boundary extraction in image processing refers to the identification of the edges or boundaries within an image. It is often done by performing erosion on the image and then subtracting the eroded image from the original. The process of erosion and morphological operation involves convolving a kernel with the input image. For each pixel in the image, the kernel is centered on that pixel, and if all the pixels under this kernel are 1, the original pixel is left as it is, usually 1 for binary images. If any pixel under the kernel is 0, the original pixel is set to 0. This operation will erode the boundaries of the object in the image where the object is represented by white pixels, since those are the pixels for which there is at least one black pixel in the neighborhood defined by the kernel. This is why erosion is set to remove white noise and shrink the size of objects in an image. As far as the code is concerned, the objective of eroding is achieved by cv2.erode and cv2.subtract, because cv2.subtract helps us to subtract the eroded image from the original image, and we of course use kernel as the structuring element. So in the context of the code that we ran, the pixels that are white in the original image and black in the eroded image are the pixels that have been eroded. In the final boundary image, the white pixels represent the boundary of the original objects, which is what has been eroded away by the erosion operation. Region filling is a morphological operation that is used to fill the holes inside a connected object in an image. The main idea is to start from a known background point and then iteratively propagate its influence to the neighbors. We will use this image for region filling. The most original image is of course this colored image, and we have converted the color image into the grayscale and resized it for optimal processing. Essentially, there are 4 steps involved in the region filling process. First, we invert the binary image. To fill a region or an object, we first need to know what is not the object. That is why we invert the binary image so that the object is now black and the background is white. Black is represented by zeros and white by ones. The next one is choosing a seed point. We need a known background point to start the region filling process. This point should be somewhere in the region that needs to be filled. All the black points connected to the seed point are considered part of the region to be filled. The third step is about propagating the influence. We do a dilation operation on the seed point and intersect it with the inverted image. This process is repeated until it doesn't change the image anymore. The dilation operation expands the seed to its neighboring pixels, and the intersection with the inverted image ensures we don't go outside the object boundaries. Finally, we combine the result with the original image and display it. We are going to look at 2 morphological operations in this session: finding contours and convex hull operation. Finding contours in an image is a common task in image processing and computer vision. While this is not exactly a morphological operation, the process often involves morphological operations as a pre-processing step to improve the accuracy of the contour detection. Contours can be thought of as a curve joining all the continuous points along the boundary having the same color or intensity. The contours are a useful tool for shape analysis and object detection and recognition. Here, the code first converts the image to grayscale, then to a binary image. It uses dilation and erosion operations to reduce noise in the image. It then uses cv2.findContours function to detect the contours in the image. The function returns a list of all the contours detected. Each individual contour is a NumPy array of x, y coordinates of boundary points of the object. The contours are then drawn on the image with the cv2.drawContours function. The -1 argument tells the function to draw all contours. The areas marked in green in the output image represent the detected contours in the image. In the context of image processing, a contour can be seen as a curve that connects continuous points along a boundary that share the same color or intensity. Here the color is set to 0, 255, 0, which corresponds to green in BGR color space, and the thickness is set to 2. By looking at these contours, you can get an idea of the objects detected in the image. The contours serve as a concise representation of the shapes in the image and can be used for various purposes like object detection, object recognition, or shape analysis. And coming to convex hull, in morphological image processing, the convex hull operation can be considered as a specific type of morphological transformation. The convex hull is the smallest convex polygon that contains all points of a shape. In the context of an image, it is the smallest convex contour that encloses a particular object or contour in the image. The convex hull operation is typically used in image processing for object recognition or shape analysis. For example, it can be used to identify and eliminate the concave regions of an object for certain applications where only the general outline of the object is of interest. In Opencv, the function cv2.convexhull is used to find the convex hull of a contour. The convex hull can be drawn onto the image or used for further analysis. One common use of the convex hull in image processing is for gesture recognition, where the convex hull of a hand can help identify different hand shapes or gestures. It is important to note that while the convex hull is often used in conjunction with morphological operations, it is not itself a basic morphological operation like erosion or dilation. It can be thought of as a higher level operation that often forms part of a larger image processing pipeline. Now, a basic question: why do we use convex hull? Convex hull is the smallest convex polygon that contains all points of a shape. In computer vision and image processing, it is often used for shape analysis and to perform operations such as object recognition or to correct for shape distortions. When we compute the convex hull of a shape, what we get is a set of points that constitute the vertices of this polygon. This set of points is often represented as an array because arrays are very efficient and convenient way of storing and manipulating a collection of elements. In this case, the points of the convex hull, especially when using a language like Python with libraries like NumPy. Therefore, a hull array is used to store these points and also to pass these points to other functions or methods such as drawing functions. This allows us to manipulate the convex hull as a whole, perform operations on all points at once, and maintain the order of the points, which is crucial for correctly interpreting the convex hull. In this code, cv2.convexhull is used to find the convex hull for each contour. And you see we have used a for loop because we want to identify the convex hull for each contour, and then cv2 dot draw contours is used to draw these hulls on the image. The hulls are drawn in blue color in VGR color space. Image segmentation is the process of partitioning a digital image into multiple segments, often with the goal of simplifying or changing the representation of an image into something more meaningful and easier to analyze. Essentially, it is a process that categorizes every pixel in an image to a particular class or label so that pixels with certain label share certain characteristics. There are many different methods for image segmentation, and the choice of method depends on the specific application. Here are some common types of image segmentation techniques. Let's go through them one after the other. We will start with thresholding. This is the simplest method of image segmentation and often used for images with high contrast. It separates an image into regions based on pixel intensity levels. The next one is region-based segmentation. This includes techniques like region growing and region splitting, which aim to group pixels that are connected and have similar pixel values. The next one on the list is edge detection. This involves identifying points in an image where pixel intensity changes sharply or as discontinuities. The points where pixel intensity is a local minimum or maximum are typically organized into a set of curved line segments termed edges. Next, we will see clustering methods. Techniques like k-means clustering, hierarchical clustering, where an image is partitioned into clusters based on pixel intensities or color. That's how the clustering methods operate. The next one is watershed segmentation. It is a mathematical approach that treats an image like a topographical map with high intensity denoting peaks and hills and low intensity denoting valleys. In semantic segmentation, we classify each pixel in the image into a class, typically done in the context of machine learning, where a model is trained to understand the context of an image. Last but not the least is instance segmentation. This not only classifies each pixel of an image to a specific class, but also differentiates between different instances of objects, even if they belong to the same class. These techniques can be used in a variety of applications, from medical imaging to autonomous vehicles to identifying and isolating specific regions of interest within them. Let us now look at edge detection a bit more in detail, and we will also develop a computer program to deploy edge detection. Edge detection is a critical operation in computer vision and image processing. It is used to identify the boundaries of objects within images, and we accomplish this by looking for areas in the image with intense color changes, which typically correspond to edges. Basically, there are two types of techniques when it comes to edge based image segmentation. One is Sobel edge detection, and the other is canny edge detection. Sobel edge detection is a straightforward and computationally efficient method for edge detection. It operates by convolving the image with a pair of 3 by 3 kernels. These kernels are designed to respond maximally to edges running vertically and horizontally relative to the pixel grid. One kernel responds to edges running vertically and the other to edges running horizontally. The kernels can then be combined to find the absolute magnitude of the gradient at each point and the orientation of that gradient. However, the Sobel operator is quite sensitive to noise, and it may produce thicker edges as it could find multiple responses for a single edge. Canny edge detection, on the other hand, it's named after its creator, John F. Canny. It is more sophisticated and performs better than the Sobel operator in terms of detecting true positive edges. The Canny method involves several stages, including applying a Gaussian filter to the image to smooth out noise, computing the gradient of the image, non-maximum suppression to eliminate any unwanted pixels which may not constitute the edge, and finally a double threshold is applied for edge detection and edge linking. This results in well-defined thin edges that are likely to fragment. So in terms of complexity, Sobel is simpler, but Canny is more effective. While Sobel may be more suitable for real-time applications where speed is more important, Canny performs better in scenarios where you want more precise and well-defined edges. Ultimately, the choice between the two would depend on the requirements of the specific application. If we need quick and decent results, Sobel might be our go-to. However, if you want more accurate edge detection and have the computational resources, the canny edge detection algorithm would be the more appropriate choice. Let us now see canny edge detection in action. We first import the necessary modules. CV2 is the Opencv library, NumPy is the library for handling operations, and matplotlib is for plotting. The imread function is used to read the image. The second argument 0 specifies that the image is loaded in grayscale. We now apply the canny edge detection algorithm to the image. 100 and 200 are the min-val and max-val respectively. Edges within intensity gradient more than max-val are sure to be edges, and those below min-val are sure to be non-edges. Hence they are discarded. Those who lie between the two thresholds are classified edges or non-edges based on their connectivity. We then display the original image and the edge detected image side by side. Subplot 1 to 1 indicates a subplot grid of 1 row and 2 columns on the first plot. The original image is displayed in grayscale. X ticks and Y ticks are set to empty, meaning no grid lines or numbers will be shown on x-axis and y-axis. The next subplot 1 to 2 indicates the second plot in 1 row and 2 columns grid, where the edge detected image is displayed in a grayscale with the title Edges. Now let us look at the code for image segmentation based on thresholds. Here also we start by importing the necessary modules. The function cv2.threshold is used to classify pixel intensities. The pixel values of the grayscale image are compared with the threshold value of 127. If the pixel value is more than 127, it is set to the maximum value 255, which corresponds to white. If the pixel value is less than 127, it is set to 0 or black. This operation converts the grayscale image into a binary image, making it easier to separate objects from the background. Finally, we display the images. Now, I want to ask, why did we choose the threshold value of 127? There must be some reason to it. The threshold value is chosen depending on the application and the specific image processing task. Of course, that is known. But why did we choose 127? The value 127 is chosen because it is approximately the midpoint for 8-bit grayscale images, which have a pixel value that can range from 0 to 255. When a threshold value of 127 is chosen, the assumption is that the image foreground and background will be approximately equally distributed in this range. In other words, pixels with an intensity value less than or equal to 127 would be considered as background and set to black, and those with an intensity value greater than 127 would be considered as foreground and set to white. This works well for images with good contrast and fairly evenly distributed foreground and background. However, if the image has poor contrast or the foreground and background are not evenly distributed, a different threshold value might be more appropriate. Advanced techniques such as adaptive thresholding might be used to determine optimal threshold value based on the characteristics of the image. Image descriptors, also known as feature descriptors, are algorithms and techniques in image processing and computer vision that assist in describing and quantifying the content of an image. These descriptors are used for a variety of applications, including object recognition, image search, and scene understanding. Typically, an image descriptor extracts information from an image or a region of an image to provide a representation that is more useful and less sensitive to variations in image characteristics such as size, rotation, or lighting condition. The information that is captured and how it is represented depends on the specific type of descriptor. Some of the commonly used image descriptors are now being explained. We will start with color histograms. Color histograms are simple yet powerful descriptors that summarize the color distribution of an image. A color histogram for an image is obtained by counting the number of pixels of each color in the image. Texture descriptors analyze the texture or the visual patterns and spatial distribution of colors in the image. Examples include heraldic texture features, local binary patterns or LBP, Gabor filters, etc. Shape descriptors are used to describe the shape of an object in an image which remains constant despite changes in orientation or scale. Examples include hue moments, Fourier descriptors, etc. Local feature descriptors are used to describe local features in an image, such as corners or distinctive blobs. The most well known local feature descriptor is the scale invariant feature transform or SIFT, but others include speeded up robust features or SURF, features from accelerated segment test FAST, and binary robust independent elementary features or brief. Deep learning descriptors are another useful technique. With the rise of deep learning, convolutional neural networks have been used to automatically learn powerful feature descriptors directly from image data, outperforming many traditional methods on a wide range of tasks. Now, let us look at the code for texture descriptor using local binary pattern or LBP. In this code, an image is read in grayscale mode. The local binary pattern of the image is computed using feature.local underscore binary underscore pattern function from the skimage library. The parameters that we use are the grayscale image, the number of points in the local binary pattern, in this case it is 8 by 8, and the radius of the local binary pattern, in this case 8 again. Both the original image and the LBP image are displayed using matplotlib. The LBP image reflects the texture of the original image. Each pixel in the LBP image represents the local texture around the corresponding pixel in the original image. LBP is a powerful feature for texture classification. Now, let us look at wavelet based feature extraction. Wavelet based feature extraction is a procedure that involves transforming an image or other types of data using a wavelet transform to extract useful features. These features are numerical representations of the image that can be used in further processing, such as classification, recognition, or comparison with other images. The wavelet transform is a mathematical tool that decomposes an image into different frequency subbands on different scales. It provides both spatial, which is location, and frequency, which is detail, unlike the Fourier transform, which only provides frequency or detail information. This makes wavelets particularly useful for images which often have localized features in both space and frequency. A wavelet transform produces a set of wavelet coefficients which represent the image structure at different resolution levels. These coefficients can be used as features that capture the characteristics of the image. For instance, texture details of the image can be captured by the high frequency wavelet coefficients, while the image's overall shape or structure can be captured by the low frequency coefficients. Wavelet based feature extraction is widely used in image processing and computer vision tasks, including image recognition, texture analysis, edge detection, and image compression. It is especially useful for tasks that require the analysis of image details at different scales or resolutions. In the code script that you're seeing on your screen, we are loading an image and applying a two-dimensional wavelet transform to the image. We are using bi-orthogonal wavelet BIR 1.3 for decomposition. The results of the decomposition are the approximation and detail coefficients. Approximation coefficients represent the low frequency components of the image, while the detail coefficients LH, HL, HH represent the high frequency component. In the plot, we are visualizing the approximation and detail coefficients as images. I want to highlight that instead of bi-orthogonal 1.3 wavelet, we can use DB8 wavelet also. DB8 and BIR 1.3 are simply different types of wavelets. DB8 is the 8th order wavelet, which is longer and more complex than the lower order wavelets. BIR 1.3 is a bi-orthogonal wavelet with a certain symmetry and number of vanishing moments. A color histogram in image processing and computer vision is a representation of the distribution of colors in an image. It provides a visual summary of the colors present in the image by quantifying the colors into a finite number of bins and then counting the number of pixels that fall into each bin. For an RGB image, a color histogram can be three-dimensional, with each dimension corresponding to either red, green, or blue channel. Each dimension will have a range of values, typically from 0 to 255, representing the possible color intensity values. The color histogram provides insights about the image with respect to dominant colors, color distribution, contrast, and brightness. The peaks in the histogram correspond to the most dominant colors in the image. The higher the peak, the more pixel in the image. The peaks in the histogram correspond to the most dominant colors in the image. The higher the peak, the more pixels in the image have that color. Color distribution. The spread of the histogram gives an idea about the distribution of colors in the image. A wide spread indicates a wide range of colors, while a narrow spread indicates fewer colors. In a grayscale image, the histogram can give some insight into the contrast and brightness of the image. If the histogram is skewed towards the left, the image is dark. If it is skewed towards the right, the image is bright. Color histograms are widely used in tasks like image retrieval, image segmentation, and computer vision tasks like object recognition and tracking, as they provide a simple and efficient way to represent and compare images based on their color content. When it comes to coding, we start by importing the necessary module and then reading the image using cv2.imread function. The image is then converted from BGR to RGB color space using CVT color because OpenCV loads images in BGR format by default, while Matplotlib uses RGB. A for loop is used to calculate and plot the histogram for each color channel in the image. CalcHist is used to compute the histogram of the image. As part of CalList, we mention channels in square brackets. It is the index of the channel for which we calculate the histogram. For example, if the input is a grayscale image, its value is 0. For a color image, you can pass 0, 1, or 2 to calculate the histogram of the blue, green, or red channel, respectively. None that you see is used to find histogram for full image. But if you want to find the histogram for a particular region of the image, you have to create what is known as a mask image for that and give it as a mask. The number 256 is for histogram size, which again is for the full size of the image. In this session, we are going to build a deep learning model for brain tumor classification. It is a multi-class classification where there will be 4 possibilities. 3 types of tumor are there and 1 scenario of tumor not being there. So we are going to start by importing the necessary libraries for data handling, image processing, model training, and evaluation. The data set in question is available online in GitHub. So first we are going to download the data set from GitHub and bring it into the Colab environment for further processing. So we have downloaded the data set and the folder that contains all the images brain tumor classification data set. So that is the name of the folder. In that folder, you have 2 subfolders, one for testing and one for training. In both the subfolders, you have additional folders that correspond to the 4 types of classification. We then define the paths to the dataset folder and define the class labels and create a mapping dictionary for class labels. The next step is about loading the dataset. We iterate over the training and testing folders for each class label. This block of code reads the images, converts them to grayscale, and resizes them to a fixed size 224 by 224, and then appends the image data and corresponding labels to the X and Y lists. You may have this question as to why we should resize and why we should resize to this particular 224 by 224. Resizing the image to a specific size, such as 224 by 224, is a common practice in image processing and deep learning. Other benefits, of course, include consistency, computational efficiency, and ease of use for pre-trained models. We now convert the data to NumPy arrays for further processing. Converting the data to NumPy arrays is important because it provides a convenient and efficient way to work with numerical data in Python. Converting the image data to NumPy arrays allows for efficient and flexible data processing, manipulation, and integration with deep learning frameworks and libraries. We then split the data into test and train. Next comes building the model. We will build a convolutional neural network model using the Keras sequential API. The model consists of convolutional layers, max pooling layers, and dense layers with ReLU activation. The output layer uses softmax activation for multi-class classification. We compile the model with the Adam optimizer and the sparse categorical cross-entropy loss function. Since the labels are integers and accuracy is used as the evaluation metric. We train the model using the training data and the number of epochs is 10. The training history is stored in the history variable and the training data is passed to the model with an additional dimension for grayscale images. Some more details on the CNN model. The first layer is a convolutional 2-dimensional layer with 32 filters of size 3 by 3 using the ReLU activation function. It takes input images of size 224 by 224 pixels, which we resized earlier, and applies convolutional operations to extract features from the images. The second pooling layer is a max pooling two-dimensional layer with a pool size of 2 by 2, which downsamples the future maps to reduce spatial dimensions and extract the most important features. The third layer is a flattened layer, which flattens the two-dimensional feature maps into a one-dimensional vector, preparing them for the fully connected layers. The fourth layer is a dense layer with 64 units and the ReLU activation function, which applies a linear transformation to the input data. The final layer is a dense layer with the number of units equal to the number of classes, which is 4 in this case, using the softmax activation function. It produces the final output probabilities for each class. The model is compiled using the Adam optimizer and the sparse categorical cross entropy loss function. During training, the model is trained for 10 epochs on the training data using the specified optimizer and loss function. The accuracy of the model is evaluated using the test data, and the predicted labels are compared with the true labels to compute accuracy. Classification report and confusion matrix are generated to provide detailed evaluation metrics and visual representation of the model's performance. Additionally, the accuracy of the model during training and validation is plotted across epochs to visualize the learning progress. As we can see here, the model accuracy has consistently improved across epochs. For the purpose of accuracy, we are using precision, recall, and F1 score. Precision measures the proportion of true positive predictions out of all positive predictions. A high precision indicates a low false positive rate. Recall measures the proportion of true positive predictions out of all actual positive instances. A high recall indicates a low false negative rate. F1 score is the harmonic mean of precision and recall and provides a balanced measure of both metrics. It considers both false positives and false negative. Support that you see here represents the number of instances in each class. Now let's try to understand the numbers, and we will do that with the help of the results we have obtained for glioma underscore tumor. A precision of 91%. What does it mean? It means that 91% of the predicted cases are true positives. 83% recall. It means that 83% of the actual cases are correctly identified. Now come to the F1 score, the balanced measure of precision and recall, which is nothing but the geometric mean of precision and recall, is 87%. Support, it shows 214. That means there are 214 instances. That is 214 instances of that particular type of tumor in the test set. Despite having fewer number of images in our data set, the accuracy of the model is very good and it has improved over epochs. It is always ideal to consider metrics like precision, recall, and F1 score in addition to looking at the model accuracy metric.